Okay. Uh, I've never lectured wearing a hat before, and I don't think I'm going to try that now. You might get a little discombobulated. Uh, it's a great honor to be asked to speak in the Simon's Science Series. It's a real pleasure to be here in this wonderful auditorium and to see so many old friends and, unfortunately, experts in geometry. Let me start out by saying this talk was not intended for you. This talk was intended to try to explain in very physical and as visceral terms as possible a basic concept that plays an underlying role in many things in mechanics and physics and differential geometry, and try to give you a sense of where it comes from, what it does, and just a hint towards the end of what the current research is in this area. Let's see, let me get this thing oh. That's not good? Okay, there we go. Okay, slight change of title, but that's the basic idea. So I'm going to try to avoid, mathematics tends to be organized towards efficiency, so that one can do lots of computations, get your hands on things, and define things very precisely. Today, I'm going to kind of ignore all of that advance and try to do things as conceptually as possible and avoid any serious computation and also avoid any precise definitions. So you may have to be a little generous, particularly the critics in the audience. But I hope that if things aren't clear, one of the things about speaking intuitively and metaphorically is that one man's metaphor is not necessarily another's meat. So in case you don't understand something, feel free to ask and speak up. And those of you who do know where I'm headed, feel free to kibitz, because I was promised that there would be people that would ask questions and talk. So I'm expecting it. In fact, I depend on it. And the physical motivation I want to start with, because it is a very physical subject. Really, the word holonomy was first seen in mechanics, and it didn't really come into geometry until considerably later. And the illustration that I want to start out with is the description of the motion of a cart. Like this cart that we happen to have here, classic two-wheeled dolly, that its position in the plane is described by basically you need three numbers to describe the position in the plane. You need say I call it the hitch, but it might be called the handle, the x and y coordinates, or the a and b coordinates of the handle, and the angle that it makes with some fixed direction. Those are the three numbers that you need to describe it. So the position space for a cart, say on the plane like this, is actually a three-dimensional space. But you can't actually, under normal operation of a cart, you can't actually move in all three directions. If you look at what's happening, and here I'll draw a little picture. Here are the wheels. Yes, I can raise it even further, and I'm going to take advantage of the fact that it's well adjustable. So the handle's here, and the center of the axle is here, and like most, I'm going to use geometric units where the tongue has length 1, and here's our angle theta here, with some fixed direction. That completely describes the position of the cart. And the condition is that, of course you can't really slide the wheels side to side very well. The point is that as the cart moves, the velocity of this point, xy, it has to be perpendicular to the axis. In other words, it has to fall somewhere along the tongue. And what that means is that if you're thinking of a curve, x of t, y of t, the velocity has to be parallel to this cosine theta, sine theta. And of course, they're functions of t. Sometimes I'll be lazy, I won't write the of t. and the condition that says that this is parallel to this, we usually remember theta x dot minus cosine theta y dot is 0. But we're not actually controlling things by moving the center of the axle around. We're actually controlling things by moving the handle around, the hitch. And of course, A and B are, because by this, is x plus cosine theta, y plus sine theta. And the rolling constraint, this no sideways slip, when you write things out, you have this is what I wrote before, but when you express it in terms of A and B, when you plug these formulas in, differentiate, you express it in terms of A and B, what it says is that theta changes, theta satisfies a differential equation. That is, if you know A and B, of course you know their time derivatives, and now theta is required to satisfy this first order differential equation. So once we know where theta is at any given time, and we know how we're going to move the handle, we know how the cart's going to move. Right? So this is the kind of rolling constraint that happens in this three-dimensional space. You can only really move in sort of two directions at any given time. There's three velocities, x dot, y dot, and theta dot, or a dot, b dot, theta dot, but they have to satisfy some linear relation. You can only move in sort of a two-plane at any given moment. But that doesn't prevent you from steering the cart anywhere you want it to go, right? I mean, we all have this experience that the constraint, you know, that in fact it was designed so that you could actually move it wherever you wanted to go, but you can't necessarily move it immediately where you want it to go. It's not. It's harder, for example, to get it to move over there than it is to say move this way, right? And in fact, that's exactly this business that there's only two directions that you can really move in. And in fact, if you do a little experiment to get some sense of how hard it is to change the angle, so if you take your hitch or handle at some point, and let's draw it. Let's take our origin here. So the handles that say start out at AB is 0, and here's our cart. Theta is 0. And suppose say you move it in a circle of radius r. Move the handle in a circle of radius r. What will happen to the angle? That is, suppose we actually do it like this. Well, if you just do the experiment, you'll notice that the cart, I'm moving it roughly in a circle. You'll notice that the cart actually does change in an angle, but the angle is actually considerably smaller than the distance you move the handle. Let's see, that is, if you move the handle in a circle of radius r, that's what that parameterization gives you, and you actually solve this differential equation. The solution, you can everybody who's taken a first year differential equations course knows how to write down the solution, but we don't need to know the formula for the solution. I just want to know what happens when I get to the end of the loop now, and it turns out the angle changes by about pi r squared when you do that. And that's a little strange when you think about it, because in order to get the angle to change by pi r squared, we had to move the hitch a distance of 2 pi r. That is, in some sense, moving in this direction that you can't directly go. You can get there, but you have to go almost like square root of the distance to get there. That is, it acts as that other direction acts as though it counts for 2 dimensions. So, and in fact, in a certain sense, if you're measuring volumes and distances and so forth in this 3-dimensional space, the thing that takes 3 numbers, it turns out that metrically the space actually behaves as though it was 4-dimensional, because this non-holonomic, these directions you can't actually move in immediately. You can move, but you have to sort of use 2 dimensions to get there. And so, in a certain sense, even though it's topologically 3-dimensional, it's metrically 4-dimensional. And so it's harder to steer in than you might guess at first glance. And basically, this is the reason that parking a car is hard. The dependency on when you're trying to jockey it into position, getting that last angle right, you have to move much further than you expect to have to move. And actually controlling things is harder than it looks. And of course, it can be done. We all learn how to do it. But not particularly, I guess. A baby carriage is the same kind of thing, as long as it has wheels here. This formula, by the way, this pi r squared is only good for small values of r. Once r gets large, it starts falling off. For example, if r is 1, so that you're actually going in this. If r is 1, you're actually going in this circle. Then what happens is that the angle is actually 0. Well, it's 2 pi, but 2 pi is 0. So this formula is only good for small distances, and to actually understand the behavior of distance when things get long turns out to be somewhat tricky. And in fact, the understanding, for those of you who know a little bit about geometry, understanding the cut locus in this geometry, that is, when things that look like they're the shortest paths stop being the shortest paths, that turns out to be very subtle. And I'm not going to try to explain that today, but I just want to point out that there are even in this simple model there are issues that require some understanding. I want to contrast this now with another kind of 3-dimensional space with a motion constraint that to emphasize that this really is something about the geometry of the way the motion constraint is working. And that's the case of, let's suppose we have a position space for, say, a planet orbiting the sun, or a bug flying around a lamp. When we were kids, we always thought that bugs were attracted to light, but in fact, they're not particularly attracted to light. What happens is that, that would be a dumb thing for them to do, right? That makes them more vulnerable to predators and so forth. Actually, what they're trying to do is navigate by keeping the light source, which they think is the moon, at a fixed angle to their path, right? So they try to do that, and if you do that so that your velocity vector is always perpendicular to your position vector, then what you find out is, well, of course, this is the condition that the velocity vector is perpendicular to the position vector, and that just happens to be the time derivative, well, 1/2 the time derivative of x squared plus y squared plus z squared. So in fact, if you do that, then your distance from the origin stays constant, and so you can't actually get everywhere in space. You're constrained to lie on level sets of this function, x squared plus y squared plus z squared. But at first glance, it looks like a very similar kind of constraint. We have a 3-dimensional space we're moving in, and we're constrained at any point. We can only move in 2 directions. But that 2 directions, the geometry of that constraint is very different from the geometry of the rolling cart. Both 3-dimensional, both one constraint, but completely different behavior. And this, of course, was noticed back in the probably noticed by Euler, but it wasn't really named until the 19th century, or at least we don't have an official name for it until the 19th century. Comparing these two different kinds of constraints. For the cart, if you have a velocity constraint, it doesn't actually constrain the position. It makes it harder to get where you want to go, but it doesn't prevent you from getting there. Whereas for the planet or the bug, that kind of simple, different velocity constraint actually constrains where you can go. Now, this second kind of motion, where the velocity constraint actually tells you, puts some real finite constraint, algebraic constraint in this particular case, on where you can go. That is an exact law that tells you where you can go and where you can't go. This kind of constraint was called what is now goes under the name holonomic constraint, and it comes from this basically Greek exact or complete and nomos for rule or law, saying that you have a velocity constraint and it implies some actual exact rule that says where you can go and where you can't go. It dates from, I believe the first mention is in Poinsot early in the 19th century in his study of tops, and then Heinrich Hertz late in the 19th century wrote a treatise on the geometry of mechanical systems like this that have this kind of actually non-holonomic behavior. The motion of the cart is said to be non-holonomic because it doesn't imply any exact law, whereas the planet motion is said to be holonomic. And that's where in mechanical systems, this is where you see where these words come from, and this is the basic dichotomy in constrained mechanical systems that we want to explore and understand, and see where it shows up in modern geometry and analysis. Okay, I feel like I'm going really fast. Any questions? Okay. Well, I want to give another example of a non-holonomic system that will actually illustrate a few other properties that we're going to need later on when we understand it in greater generality. I was at Duke 20 years, and as David said, I'm now that I'm about to step down from being director at MSRI, I'm returning to Duke, and so.
Connection between Duke and basketball?
Beats me. So, right. Yes. What I want to consider is another mechanical system that actually turns out to have a lot of relevance to modern technology. The problem of understanding a ball rolling on the plane without slipping or twisting. Two places where this shows up these days. One, a lot of people are familiar with is trackballs. When you have some 3D object on your computer screen and you want to rotate it and around, what you typically have is a trackball that you can push in one direction or another. What you can't do is turn it, right? Or at least you can't do it very easily. What you can do is just push in some direction. Now, of course, I'm letting the trackball move, but the main thing to think about at the moment is in that model is the orientation. The other application that comes up is in robot handling of objects. Typically the robot handling of objects is the hand is a very simplified hand. It doesn't look like ours. It's two plates, and the plates come down. They grab the object, and it may not be in the right orientation, but the plates can move relative to each other. and allowing one plate to move relative to the other rolls the object on the bottom plate, say, and changes its orientation. So you can orient it and set it down somewhere. That's the engineering problem where they really spend a lot of time trying to find good algorithms for doing this. Of course, nothing they do is as flexible as our hands, but then we're not trying to build general purpose machines. We always have some specific thing in mind. So, but it does raise the question. Obviously, you set a ball on the table and you roll it from one position to another. How do you describe that mechanical system, and how controllable is it? So the mechanical system now, we've moved from 3 dimensions to actually 5 dimensions, because you can describe it a number of ways, the actual possible positions of the ball. One is you need 2 coordinates for where the ball touches the plane. And the other is you need, it turns out, 3 coordinates to tell you how it rolls. Now, coordinates turn out to be a very bad thing in this context, because the space of rotations, which is what we're trying to parameterize, it is. I mean, intuitively you can see that it's 3-dimensional simply because you all know about pitch, roll, and yaw. So infinitesimally there are 3 conditions. Another way you can see it is one way to describe the position, the orientation of the ball, is to say what point the ball touches the plane. And that's 2 parameters because the surface is 2-dimensional, and then what angle it is. So that's a 3rd direction that describes the position of the ball. But the thing I want you to think about is the way I really want to think about it is describing the position is where it touches and what orientation it's in. And that orientation, the set of rotations is an object that's going to be important in what we talk about for the rest of the time. The set of rotations is what mathematicians call a group. That is, if you take one rotation and follow it by another rotation, the result is yet a 3rd rotation. That is, take 2 rotations, you can multiply them, and you get a 3rd rotation. There's a natural way to multiply rotations. And I'll think of the reason I call it A is because, of course, in mechanics books, they call that the aspect or the attitude matrix that says how it's oriented, what its attitude is. And you multiply 2 attitude matrices, and it tells you how the composite rotation of the two happens. Okay, so what is the constraint, actually, when you roll like this? Basically, as you're describing the point of contact as it moves on the surface, and that completely determines how the ball is going to roll, because we're not allowing it to twist or slip. And so I'll write down the differential equation for those of you who want to see it. If x and y if you have a path given by the point of contact moving and the attitude matrix, that is the element in the orthogonal group, then it turns out that they're related by this equation, which says that the rate at which the attitude matrix changes is the attitude matrix itself times this skew symmetric matrix given by the derivatives of x and y. It's an easy exercise in calculus to sit down and actually work that out. I didn't want to spend a lot of time on that because I wanted to spend more time thinking about the consequences of this. So and besides, I hope I'm going to be able to convince you with the ball of the things I'm going to tell you that otherwise I'd have to demonstrate by solving differential equations. So let me see if I can do that. The main thing to think about is that, again, we're talking about, we're moving now in a 5-dimensional space, but it's now subject to 3 constraints. So again, at every point in this 5-dimensional space, we can only move in 2 directions. And the question is whether or not with those two directions you can actually get, is it possible starting in a given position and orientation to roll over here and wind up in the orientation that you want to be in and in the position that you want to be in. So we're trying to steer in 2 dimensions but navigate in 5. That's what so we've kind of upped the ante a bit. And correspondingly, it turns out it's a little harder. It's harder than doing that. If you sit down and experiment a little bit, you'll find, well, all of us have learned how to master a hand cart. That's not so much trouble, and a lot of us can parallel park. But if somebody tells you, move this ball from here to here and have it turn up in this orientation, you may sit and figure, and you may find yourself fooling around quite a bit before you can get there, because you're actually, like I said, trying to navigate in 5 dimensions when you only have 2 dimensions of freedom at each point. And so this is the question. Is it possible, actually, to get from any place to any other and get in the right orientation? And there's a separate question about how hard it is. And if people are curious, I can tell you something about that. But that may take us a little bit further afield.
So that question would be sort of, how far do you have to roll it from the origin to?
For example,
to get
yeah,
back to where you
that's
wanna
right.
get?
For example, you might ask, how long of a curve do you have to roll over to get into this position with the given orientation, right? And it's distressingly long. It's one of the reasons engineers have to fool with this and worry about it. So,
but you can do it.
Yes, I'm gonna argue that you can, and your intuition is right. You can do it, but now I want to try and explain why without actually doing the calculations. Right? The key thing to keep in mind is that, as I said, the rotations form a group. That is that if you have a rotation. You can compose 2 rotations, and I'm going to say a little bit about how that's affected by the rolling. The other observation that I want to make is that if you do have a rolling path, that's what I'll call it. It's a path that satisfies the constraints. A rolling path with a given. I do have here somewhere yes. This thing, right? If you do have a given path with rolling, and you take any constant rotation matrix, and this is why I put up the equations. I just wanted to convince you of this: that if you just right multiply, and it's important that it's right multiply, not left, because multiplication in this group does not commute. If you right multiply, then this is also a rolling path. And the reason is, if you plug in AT times a constant here into this equation, well, when you differentiate this matrix product, it's A prime times C plus AC prime, but C prime is 0, so you can actually just pull the C out. And so this part, which is 0, even when you multiply by C, stays 0. And so right multiplying by a constant matrix always also gives you a rolling path.
Isn't that just moving the ball to a different place before you start?
It is. That's right. And intuitively, that is exactly what the point I wanted to make, which is that the consequence of this is that if you take any rolling path, if you start with a curve in the plane, and you want to know what is the effect of the curve on the rotations, then it turns out that it doesn't matter what attitude matrix you start with, if you take the end attitude and multiply by the inverse of the beginning attitude, that is independent of what your initial condition was. So that rotation, that rho that's associated to this gamma, is independent of any choice of rotation. It's something intrinsically associated to the path. right? And that wouldn't be true if we didn't have this fact. So that's
It's independent of any initial,
it's independent of the initial attitude matrix. If the initial A, that's right. So you have a choice of a 3-parameter family of A's for any. When you start, you decide how you're gonna rotate it. Then you roll it along your path, and it rotates. And the difference between this rotation and this rotation, done in the right order, and that's crucial. Done in the right order is independent of how you actually started the ball rotating. Right. Okay. That's right. It's independent of which actual orientation or attitude matrix you started with. It's a rotation that depends exactly only on the curve in the plane. Right. Now, so we have a way of taking curves in the plane. So actually, to be honest, they have to be differentiable curves, otherwise this won't work, but let's assume they're at least piecewise differentiable. For each curve in the plane, we have a way of associating a rotation matrix to it. And that comes out of the rolling constraint. So, I just want to say what some of the properties of this rotation matrix associated to a path are. I mean, at first glance, this is a little strange because, I mean, paths in the plane don't look like they have anything to do with rotation matrices. But this device transforms one into the other, and there's a few properties I'm going to need in order to do my argument. One of them is that if I change the path continuously, then the rotation matrix will change continuously. And it's intuitively believable in the sense that so here's one path, say gamma t0, gamma t1, and if you, for example, were to retract the path to a straight line, and you change this path continuously, the theorem that says it is continuous dependence on parameters for ordinary differential equations. But intuitively, you can imagine that if you change the path just a little bit, then the ending result rotation will change only a little bit. And in fact, there's a bound, and when you're trying to be precise. In mathematics courses, we estimate that change and we prove continuity, etc. But I hope you'll believe me that it's continuous.
These are differentiable paths, or do they have constants? No.
They're allowed to have, say, a finite number of corners, say piecewise differentiable. Then you can solve the differential equation along each piece that's differentiable and use that for the next initial condition and keep going. So, and you're right, you might worry a little bit as you straighten out a corner. Maybe the variation will depend a little bit too much on the corner, but it's okay. It turns out, I mean, this is what we have. This is why we prove theorems. So, it depends continuously on gamma. The other thing is that you'll notice that in the formula, I only used the derivatives of x and y. So it didn't really matter if I add a constant to x and y. If I translate the path, it doesn't change the rotation. So two paths that differ by translation will be associated to the same rotation. The third thing, again, this is intuitively obvious, but you actually have to, you sit down and do the calculation. If you roll along a path and get one rotation, and you roll back along the same path, you'll get the opposite rotation, the inverse rotation. And finally, if you concatenate two paths, that is, if you have gamma 1 and gamma 2, gamma 2, then, again, this is almost a tautology, but not quite. If you now make a new path that's the concatenation of the two paths and look at its rotation, then the rotation that it induces is just the product of the two rotations of the two paths. So these kinds of things, it tells you that, it's sort of like, those of you who know a little algebra, it's sort of like saying we almost have a homomorphism from paths from paths in the plane into the group of rotations. The only trouble is paths in the plane aren't actually a group, and so there's not really a something like that. But still, it's still it gives. It's close enough that we can use it to actually derive some results. So, and let's see what some of those results are. One thing that here's one thing that's worth thinking about is that if you look at the set of rotations that you can get by rolling around in a loop, that is a path that starts and ends at the same point. If you look at that set of rotations, that set of rotations is it's connected because any loop can be contracted to a point, and that's continuous. So you'll be continuously moving back to the identity. So the identity rotation. So the set of rotations you can reach is connected to the identity. It's not some misty, totally disconnected set inside the set of rotations. It's a nice connected set. The second thing is that because if you compose two loops that starting and end at the same point, compose those two loops, you'll get another loop that starts and ends at the same point. And if you reverse a loop, it's still a loop. So this set is closed under multiplication and inverse. And finally, if there's one point in the plane such that when you roll around the various loops and come back, you can get every rotation, then it's going to be true for all points in the plane. And not only that, it'll be true that starting at any point you can get to any other point. Right? So any position in the five-dimensional space, you can get to the position in the five-dimensional space. So it's enough to show that there's one path, to show that there's a point that for which, when you roll around in loops, you can actually get every possible orientation. The tricky thing at this point is that I have to call on a real theorem that, if you think about it, I hope you'll agree it's intuitively clear, but I don't want you to fall in love with it too much because it's not going to be true in higher dimensions. But at least in our three-dimensional world, it's going to be true, which is that it turns out that the rotation group in dimension 3 has this property. It's kind of a really nice property that tells you what the sets are that are closed, connected under multiplication and inverse, and there's only three possibilities. One possibility is that it's just the identity element. The next possibility is that it's the rotations about some fixed axis. Obviously, if you have two fixed points, and you compose two rotations that fix those points, that those rotations will fix the point, and the inverse will fix the point. So rotations about any fixed axis will give you such a subset. And the theorem is there's nothing else except the whole rotation group. Those are the only three possibilities. It's either rotation about an axis, the identity, or the whole group. Now,
The key thing is that it's closed under multiplication.
it is closed. Yes, right. Yeah, we need that it's closed under multiplication, and we need connected too, because you could take, say, there's this classic, those of you who've ever heard about the Banach-Tarski paradox, that you can divide a sphere up into 5 pieces so that 2 of the pieces can be reassembled into a solid sphere of the same radius, and then the other 3 can be assembled into a solid sphere of the same radius. That theorem depends on being able to construct a subset that's closed under multiplication and inverse that's dense and weird. It's totally disconnected, but it's dense and weird, and it's used to divide up the sphere in a funny way. I know it sounds, everybody believes this is impossible at first glance, but this can actually be proved by using these weird subgroups. But this connected really throws that out the window. Basically, connected tells you your intuition is good. Anyway, so now using this theorem, it's easy now to check that the set of rotations we can reach with a ball is neither the identity nor rotations about a fixed axis. All you have to do is, well, one thing, you just roll like this, and it's clearly not the identity. And if you roll in a different direction, you get rotation about a different axis. So it's not rotation. It's not this one and it's not this one. So the only thing left is this. So it must be possible to actually roll from one place to another, get anywhere you want to go by rolling without slipping or twisting. Notice that this is completely constructive, completely non-constructive. It doesn't give you any hint about how you would actually do it. It just says that it's true. And that's unfortunate. It's no good for engineering. You need to know more than that. The other objection you might make, and it's a reasonable objection, is that it's really easy to cheat with a basketball, right? I mean, I'm saying I'm rolling without twisting or slipping, but I've been practicing, right? And I could be subtly rotating things and so forth. You'd actually have to go home and practice to make sure that you're not make sure that I'm not cheating. And partly to convince you that it's not a matter of cheating, and also partly because I'm going to need this, need the subject that it brings up a little later on, I'd like to take and discretize this problem. That is, I'd like to, instead of having a ball, I'd like to have something that has only a finite number of possible positions that we can actually see with our eyes exactly what happens when we roll. And it's not too hard to come up with things like that. For example, there's an approximation to the ball. Not a very good approximation, I'll grant you, but at least it's nice and symmetric, and it's easy to tell how it's oriented and so forth. But I still could cheat a little bit by doing this kind of slipping around on the table. So I actually prepared a test a test plane to do the rolling on. And so, of course, for a tetrahedron like this, if I, rolling it, that is flipping it over as I move from one place to another, is just going to move on this tessellation of the plane, on this tiling of the plane. And it'll be really easy to tell whether or not I'm cheating. Right? Now, notice that, let's see, let me check that. See how I'm doing. Oh, yeah. Notice that the red one is down, and yellow is on the left, blue is on the right, green is on the top. If I roll in a loop, for example, like this, roll in a simple loop like that, does it rotate? It's the identity. In fact, here's a little thing, something that I didn't tell you. I mean, you might say, well, that was only one loop. Suppose I go like, and
No rotation.
no rotation, right, yeah.
Very strong pull.
That's right, yeah. It's exactly. Although I have a confession to make. The group of rotations is not called the non-holonomy group, unfortunately. It's called the holonomy group. This is a confusion of terminology that has driven many people nuts. But unfortunately, the holonomy group measures the failure of holonomy. So that's the thing you have to think about. But in fact, I only have rolled it in a few simple loops. But actually, these properties that I was telling you about actually show that it's enough to figure out what happens when you roll around a single loop. Because any loop, draw it really quickly. If I were to go, for example, in this path, one thing I could do is simply do this instead of, so go like, see if I can say this right. Oh yeah, so for example, instead of going around like this, what I can do is backtrack like this, and it becomes this loop, and then followed by this loop. So it can be decomposed into two loops, and in such a way that the multiplication works out. That is, the rotation associated to each loop is it just multiplies. So, and in fact, any loop, no matter how complicated I write it like this, can be written as a composition of simple loops and backtracking, simple loops and backtracking. And the result is that it's enough to check what happens when you go around a simple loop. And we've already seen that that doesn't do anything. So in this particular case, this approximation, unfortunately, is not very convincing. And so I'll make a little chart. The tetrahedron, the symmetry group, and the holonomy group. The symmetry group is the set of possible orientations when it's here. Because this is discrete, I've also made the rotations discrete. And it's easy to see how many symmetries there are. That is, how many ways can I put this down so that it fits on this triangle? Anybody? 24 ways, because there's basically 4 faces. Each one can be put down 3 ways. 4 faces each way. So it's 12, right? So 4 faces. And in fact, that set of the symmetry group, it has order 12, and it actually turns out to be the permutations of the vertices, but it's only the even permutations of the vertices. If you wanted to get...
You're ignoring inversion.
That's right. I'm ignoring reflection, because that's not a right. Yeah, a reflection, for example, would allow me to exchange these 2 vertices, but left-handed and right-handed are not the same. So the symmetry group is actually the alternating group on 4 letters, has order 12, but the holonomy group is trivial. It's only size 1. Well, the hexahedron, otherwise known as the cube, the hexahedron, how many symmetries does it have? How many ways can I put it down on in a position like this?
24.
There are 24, 6 faces, 4 ways each face, right? And so it's 24, and 24 seems like 24 is a well-known number, and you can think of it as permutations of 4 things. It's actually a symmetric group on 4 letters. Symmetric group on 4 letters is 24 of them. And what are the 4 objects? The 4 objects are actually the opposite pairs of vertices. There are 8 vertices. They come in opposite pairs. So if you look at sets, pairs of vertices, there's 4 pairs. And every rotation, the position is completely determined by knowing which vertices, where the pairs are. Now, if you roll around say, a loop, and the loop argument's still going to work here. If you roll around the loop, one thing you'll notice is that this vertex is stuck at this corner, right? So the holonomy around that point, around that loop, is actually a rotation that fixes two vertices and just is a 3 cycle on the others. So you never get anything but 3 cycles in any loop. And since it's 3 cycles and 3 cycles are all even, you don't get all possible rotations. You only get half of them. You actually get a 4, this 12. So this, you can't roll into every position either. You can only roll into half of them. So, but it's better, you know. You can get it half of them, right? The octahedron, I think a lot of people in the audience, particularly people that like mathematics, know about the duality between the octahedron and the cube. That is, the faces of the cube are like the vertices of the octahedron, et cetera, and the vertices of the cube are like the faces of the octahedron. So again, the symmetry group is again S4, and the 4 things are the opposite faces now, right? And if you now sit down and work, so again, 24 here. And again, if you sit down and work this out, you're going to have to pay attention. If I roll around this loop, remember, red is up here, green is down, yellow, blue. Any idea? Maybe I should do it again. It's a 2. That's right. In fact, what it does is it exchanges 2 pairs, right? It's exactly you know, if you label the pairs as 1, 2, 3, 4, then it's like 1, 2, 3, 4, or 1, 3, 4, 2. Or 1, 4, 2, 3. Those are the ones that you get by rolling the different things. And so, in fact, you don't get. And of course, there's if you roll twice, you get nothing. So in fact, it turns out the only thing you get is not even A4 this time. You get Z2 cross Z2. This is a group with 4 elements, and the holonomy actually went down. We're going in the wrong direction. Next, yeah. Well, now, unfortunately, polydrons don't come in 6 colors, which is about the most symmetric coloring that you can do. You can't do a symmetric 3 coloring or 4 coloring, but you know, 2 and 6 you can do, and 12, of course. But this is, you know, of course, the dodecahedron, and its symmetry group. Somebody, you know what the order is, right?
5 factorial.
It's actually 60. There's 12 faces, and there's 5 ways you can turn any face. So there's 60 of them. It's not so obvious what group it is, but when you look at the dual group, that is the icosahedron, which has 20 faces corresponding to the 20 vertices of this guy. And unfortunately, polydrons only come in 4 colors, so they actually come in a 5th color, clear, which is what this guy is. When you do it this way, you can actually see that there's a set of 5 things that the rotation group acts on. Namely, if you divide the faces up into 5 groups, that is the red faces, the green faces, the yellow faces, the blue faces, and the clear faces, then any motion you make permutes those 5 things. And it turns out that it's exactly 60. It turns out that it's the even permutations on 5 things. That's for both of these because they're dual to each other. But there's one annoying thing about the rotations for this guy is, there's no tiling of the plane that has five-fold symmetry. So if you sit down and work this out, I'm going to skip over this and kind of leave it as an exercise to figure out what happens when you roll the dodecahedron. You can't have training wheels. You have to actually think about what you're doing. So, but for the icosahedron, you can do it. Of course, unfortunately, I could have made a big icosahedron, but it's kind of unstable when you have the clear faces. So I didn't want to do that. But again, you can set this up and do the roll and work it out. And lo and behold, you work it out, and it generates all 60. So in this particular case, I'm kind of running out of time, but you do get all 60. You do get all 60 positions that you can roll icosahedron in. And like I said, I'll leave it to you to figure out what happens for the dodecahedron. Now, why did I do all this? So I should put the icosahedron up. And I put this in the wrong place, actually. Why did I do all this? One thing I wanted to do was convince you that there are many interesting subgroups of the rotation group in dimension 3, and they can show up in this kind of discrete version of holonomy. And so I'm going to leave this in existence. I'm not going to erase it, just as a sample of what happens, and go on to now talk about something that may in these moments, I have only 30 minutes left, seem like a completely different subject, but in fact will turn out to be intimately connected to what we're talking about. And that's another place where holonomy turns up, and I'll call it internal guidance systems. But those of you who know differential geometry know better by parallel transport. But let me, what did I do? Oh, here it is. All right. I wanted to do a kind of a thought experiment. And again, go back to a car, but think of the car as now moving on the plane, an actual car, and how does it keep track of its orientation? I'm going to imagine that it's kind of a crude guidance, internal guidance system. It was anemometers that have vanes in four directions. Put big heavy balls at each end so that make the pivot frictionless, so that when a car drives along on the plane, it turns, but the balls don't turn. Right? They will, by inertia, they'll stay oriented the way they're supposed to stay. So when you go traveling along some curve, when you drive the car along some curve, what will happen is at each point, the balls will continue to be where they were, even if the car is rotated. Say this is the east ball. And here, the same way. It's a very crude guidance system, and there's much better ones using gyroscopes, but it will illustrate what I want to illustrate when we go to look at now not navigating on a plane, but navigating on a surface, like the sphere, for example, like the surface of the Earth. If you, instead of taking a plane, consider a very big car or a very small planet, one or the other, and drive along the equator. And just to make things simple, let's take right angles here up to the North Pole. If you do your inertial guidance system here with the east pole, the east ball here, and we assume gravity is going to act so that it's always directed perpendicular to the surface, then gravity will, of course, cause the thing to turn, but it won't do any more than it has to. And as say the car drives along the equator, the east ball will stay pointed along the equator. And then if the car drives along a longitudinal line up to the North Pole, it will, it'll stay pointed. The North Pole, the north pointing ball will stay moving that way, and east, north, west, and south. And if you then drive back, what you'll find is that the east ball has now rotated by 90 degrees. That is, as you move, as the car turns and now navigates with the west ball leading it, it comes down and the west ball's here, the east ball's here, is rotated by 90 degrees. This is a special case of something more general. And on a flat surface, as I said, you drive around in a loop, you always come back, your inertial guidance system agrees. But on a curved surface, when you drive around in a loop, the inertial guidance system actually is ambiguous. It gives you a rotation depending on the loop that you've taken. And in fact, this I drew it on a sphere, but there's a completely general fact about if you take any surface. It doesn't have to be a sphere. And you drive around in a loop, and you follow this, always assuming that the curve, always assuming that your guidance system is that gravity is always acting perpendicular to the surface of the surface. Then it turns out that what happens is this: when you drive around in a loop, if you follow the pole, that is the vertical pole, this is always perpendicular to the surface, and you look at where that points on the sphere, and that'll be some then the area enclosed, this is on the two-sphere, these are the unit normals, then the area enclosed equals this is on the unit sphere, equals the rotation that you get, the Holonomy rotation, we'll call it. Now, this is, it's something you have to actually calculate, but it's something that has to be proved, but it's not a hard calculus thing to do. This should stimulate an echo in your mind about something. It converts kind of a curve into an area. Yeah, it's a Stokes theorem kind of thing. It's a take a boundary, exactly. But even beyond that, it has, because of the sort of the scale invariance and the way that it actually computes the rotation. There really is a dimensional change going on, and I don't want to dwell on this too much, but I just wanted to point out for people that are thinking about how could you have a length convert to an area. This is part of the whole phenomena of holonomy. But the important thing is that the holonomy, that is, whether or not the inertial guidance system is unambiguous, detects whether or not the surface is flat. If the surface is flat, then it turns out that this Gauss image, when you draw it, always encloses an area of algebraic area 0. It might have some positive, some negative, but it's always 0. So you don't actually get accurate tracking. It's when the surface is curved, like when it's convex, and then the Gauss map sort of covers positive area. When it's concave, it covers negative area. that's where you see the actual holonomy goes backwards when you on a surface of negative curvature.
But that's not if and only if.
Hmm?
That's not if and only
It is if and only if for all loops. That is, if for all loops the holonomy is trivial, then it's flat. But for some loops, it could still be trivial. In fact, you could, if the surface has some positive curvature and some negative curvature, you could take some loop that adds up algebraically to 0, and you get no rotation. Now, yeah. So this way of detecting curvature, which is those of you who've studied any differential geometry or even vector calculus, this way of detecting curvature, which depends on two derivatives, in terms of something that's not even a derivative, it's like an integral, it's a solution to differential equations, turns out to be a very fundamental link between geometry and analysis. The way we associate a geometry to a surface, or as, of course, one of our founders, the founder of Riemannian geometry, Bernard Riemann, proposed that the way we should think of geometry is that it should be a way of defining lengths of curves. That is, we should be able to tell how, we should be able to measure distance in the space, in your configuration space, and we should be able to do it by basically integrating the velocity. So you have to know what a velocity is and so forth. This generalization of Riemannian geometry, of assigning geometry to configuration spaces, generalizes this surface picture in many ways. And in fact, the generalization is not just the lengths, but this whole notion of parallel transport of inertial guidance system. If you have a way of determining your acceleration and velocity in a space, then you have a way of knowing whether or not you're twisting and turning. And I'm not going to go into detail on this because we don't have time to do the calculations, but it turns out that there's a very natural way to associate, as long as you know about lengths, to associate, to tell whether or not an inertial guidance system is tracking accurately. And again, it turns out in all dimensions that whether or not there's any ambiguity in the inertial guidance system when you track it tells you whether or not the space is flat. A very vivid example of this was demonstrated in relativity. When Einstein developed the general theory of relativity, one of the first things that it predicted was that if you could make sufficiently fine measurements, even if you took very accurate inertial guidance systems out in space and went around the sun or even around the Earth, you'd be able to detect a difference, a rotation caused by the curvature of space. And lo and behold, we now have instruments that are accurate enough to actually do that. We can actually see that, by following, really, really delicate and careful instruments, we can tell that space really is curved by doing exactly this, following parallel transport around loops. Now, I'm coming close to the end of my story, and I wanted to, briefly tell you what happened in the last 100 years. Because all this, is, in spite of the fact that this may seem somewhat new if you've never thought about it before, all this is very classical, all the stuff about rolling mechanics and computing holonomy. But the idea of understanding it in terms of groups was not really available until Élie Cartan, who Schouten was the first person, as far as I can tell, who really said that it's important to understand this ambiguity in parallel transport. But Cartan was the one who realized that you should be thinking of it in terms of groups. That is, you should be looking at the loops based at a point and seeing exactly what the group of possible ambiguities, and that would give you a measure of the curvature of the space. And he defined what we now call the holonomy group, which, as I said, measures the failure of holonomy. And actually, in a remarkable paper, his first little book on Riemannian geometry, he simply states, in dimension 4, there are spaces, which we now call Calabi-Yau spaces, where the holonomy is not all rotations, all possible rotations in dimension 4, but these particular subgroups like SU2. Now, it's not important that you know what SU2 is, but the fact that there are exotic subgroups or different subgroups sitting in, and this is what I said, is different in higher dimensions than it is in dimension 3. It turns out that as you go up in higher dimensions, there are more and more connected subgroups. Lots of different possible connected subgroups, and in fact, they put the disconnected subgroups, the closed disconnected subgroups, in SO3 to shame because there's tons of them. But in fact, it turns out that not all of them can be holonomy. There are some that are just forbidden by the differential equations that holonomy satisfies from happening, and in 1954. Marcel Berger went through the list of possible groups, and by brute force canceled off all the almost all but a very small list of possibilities for what could be the holonomy of a Riemannian manifold of a space, and it's a very long, kind of complicated paper that you get to the end of it, you have no idea why it's true, other than you did the calculations and you did all the representation theory and so forth. And Jim's not here, so I can say this. In his thesis, in fact, in 1961, he introduced some very clever ideas. This idea of holonomy systems. That actually gave a conceptual explanation for what the list was and why it should be what it was, and came up with a new proof of the possibilities that didn't depend on knowing for example, knowing the classification of Lie groups and their representations, which Berger's proof definitely depended on, and that gives you a sense right there that it would be very difficult to understand conceptually what was going on there. And next week, when we have this conference to explore the mathematical legacy of Jim's papers, there's going to be several of us giving talks about what happened to his results in holonomy, as well as lots of other things. And I hope those of you who are interested will come to those talks. But let me finish my story, since I am running out of time. It turns out that every time there is a reduction of holonomy, that is, if the holonomy is smaller than you think it ought to be, what it means is that there's some conservation law. This duality that I was telling you about between the holonomic and the non-holonomic, now in higher dimensions, it doesn't become just black and white. It becomes different grades. Some things are more holonomic than others. And the more holonomic they are, that is, the smaller the holonomy group, the better we understand the space. And the better the properties are, the better the uses we can make to them. So it's really important for us to understand which spaces allow metrics, that is, these kind of measures of distance, that have smaller holonomy. And I'm just going to list a few applications. It turns out, for example, in complex manifolds, in complex geometry, the best thing you could do to have a metric would be to have a metric for which parallel translation preserves the complex structure. And in fact, those are the manifolds that are now called Kähler manifolds, and are ubiquitous in algebraic geometry. Yau, in fact, won a Fields Medal for his work on proving that certain spaces that had not only complex structures, but holomorphic volume forms, you could actually adapt the metric to that and get the holonomy to preserve that. That turned out to be a very, at the time, daring and quite difficult feat in nonlinear differential equations. And the proof has been simplified somewhat over the years, but it still stands as kind of a landmark for the way we've married analysis to geometry to topology. And these spaces, Calabi-Yau spaces, in fact, the Calabi-Yau spaces whose dimension is 6 have turned up, in fact, they're at the heart of string theory. And these relationships with counting in threefolds with trivial canonical bundle. I know those of you who aren't mathematicians won't know those words, but it turns out that there are deep connections with arithmetic on one side and differential geometry and physics on the other that have really, for the last almost 30 years now, been tremendous inspiration for work in all those areas, and spectacular results. In the physics in Yang-Mills theory, I have not yet said the word connection, and now I'll say it. It turns out that the general setting in which these holonomy things show up is in the theory of connections that are adapted to physics. There are all sorts of ways of asking for what's the best adapted connection. Yang-Mills theory turns out to be still a very active subject with tremendous amount of work going on that and understanding the special solutions that correspond to some kind of reduced holonomy and the set of their moduli is an extremely active area in modern differential geometry and physics. One of my favorites is the successor to string theory. It turns out space could turn out to be 11-dimensional instead of 10-dimensional with 6 small dimensions and 4 normal. It could be 7 small dimensions. It turns out that those 7-dimensional spaces with special holonomy have played an important role in high-energy theoretical physics in basically the last about 30 years now. I think, and I can maybe say, this holonomy, this group that shows up in dimension 7 is one of the exceptional groups, and it was one of the ones that was on the list, but nobody knew whether or not it really happened. Whether or not maybe we just hadn't had strong enough techniques to cross it off, and in 1984, I was lucky enough to actually show that these things exist, and was able. It's sort of, in some ways, it's the analog of Cartan showing that the Calabi-Yau spaces existed back in 1926 when he did it. But that was a local theorem. The global analysis involved in these things has gone very far. Dominic Joyce, a large number of people have worked and continue to work in this area. And I just want to say, at the end, that understanding this geometry, topology, analysis has turned out to be, whether they exist locally, how flexible they are. Those problems have turned out to be a very fertile source of both problems and results since Jim's work, and it's very much an ongoing area today. And I forgot to say about the cat. I forgot to talk about the cat. Probably everybody's wondering what is it? What? Yeah, I forgot to say that. Yeah. Well, it's the picture is this, and this really will be the last thing I'll say. If you think of how does a cat turn itself upside down? If you hold it with its legs up and let it go, the cat will land on its feet, and it does not do it by simply rolling over, right? Because that would violate the conservation of angular momentum. Right? Can't do that. So, but it's got to move in some space, and it's got to be able to move in some space so that it actually can turn from having its feet up to its feet down. And it turns out that this is actually an example of non-holonomy. And the reason, and I can explain it very briefly, the model is that instead of a cat being a rigid body, what they do, very, very simplified model, is they imagine that the cat is actually well, typically they say cylinders, hinged together at a hinge. Right. So the configuration space for the cat really is, first you have the orientation of the front cylinder, the head and the tail. And then you have an angle, an extra angle that tells you how much the back is bent. And so the configuration space is actually four-dimensional. And there's a constraint. You can't move in every direction because you can't just move to, you can't just turn over because that would violate conservation of angular momentum. So what the cat does is move in the space tangent to that distribution, and that distribution turns out to be non-holonomic. And you might want, you can see pictures of it, and I'll show you one in a minute, but I think it's actually more convincing to do this. Imagine the feet are up, the hinge closes like this, and then the two cylinders turn in opposite directions so that their angular momentums cancel out. And then the hinge comes out like this. Right. And if you actually see videos of a cat falling, that it flexes its back and flips over like that, exactly like that. It does it without ever violating the conservation of angular momentum. But it's navigating in a four-dimensional non-holonomic space.
That sounds especially cruel.
Yeah, right. Yeah. Right. But I mean, and of course, the point of that story is that you don't have to be terribly smart to be able to navigate in non-holonomic geometries. They're around us everywhere, even the animal world. That's right. Yeah. Right. Yeah. And I hope that what I've said has convinced you that there's an interesting story here, that there's interesting applications, and given you a sense, if only a brief glimpse, of the kinds of mathematics that are involved in understanding holonomy and isolating this idea so that we can work with it. Okay, thanks.